So you like, these are the familiar particles, because these are the particles in your body, and these are not. Okay. So this is just to clarify our last lecture. Okay. Now, as I said, this is actually for the students that stayed till now. Now we finally begin the interesting part of the course. I'm a little bit sorry that I took 3 lectures in order to go through the background. Now we are ready to do the Cartan classification. So one thing that's very clearly, from our SU3 discussion, and that's why I spent so much time on SU3, is that the roots and the weights form a geometrical pattern. They form geometrical patterns. So the equilateral triangle, for example, comes in, the octagon, and so on. The hexagon, sorry, the hexagonal symmetry. And so this is really fascinating that out of group theory, you have geometry also. So algebra and geometry are linked in this very way, in this way. And this is what the insight of Cartan, if you like, that this is what gives us the possibility of classifying all Lie algebras. So we can ask, does it generalize? Okay, the poor man's approach, which is sort of the Landau school, Landau-Feynman type approach, is to just do another example in SU4 and try to generalize. Okay, so I give this to you as an exercise, but I will sketch how this would go. And you can just see by counting again that it works. Okay, so SU4 is, of course, it's the 4x4 traceless Hermitian matrices. So there are 4 squared minus 1 equal to 15 of such guys. And the diagonal guys are, as usual, the lambda 3, 1 minus 1, 0, 0. So we just take the SU3 matrices and add an extra 0. Now to make it 4x4, lambda 8 is 1, 1 minus 2 and 0. And there's some normalization, which we don't worry about. And lambda 15, then this is the new one. So you see these are just the 2 Gell-Mann matrices, in which the 2 SU3 matrices, but just add a 0. So they're trivially extended from SU3. The new one is this guy, and it has to be traceless and orthogonal to these. So it's obviously 1, 1, 1 and minus 3. And the normalization, in order to be normalized the same way, is 1 over root 6. Okay? So therefore, the weights and roots live in 3 dimension now. So you remember for SU2, they live in 1-dimensional on a ladder. On a for SU3, it's like a climbing wall at the gym. It's 2-dimensional, but here they're 3-dimensional because every state in the representation, a state in the representation would be characterized by 3 numbers, which are the eigenvalues of these 3 matrices. Right? So for SU3, remember it's isospin and hypercharge. But now for SU4, there's isospin, hypercharge, and something else. And people get tired of giving names to these things, so there's no name. Okay, are there any questions? Okay. So again, the one approach in physics and mathematics is to make a guess. Okay. So you remember that the roots in the SU3, the weight diagram, is an equilateral triangle. And those are the 3 quarks. And we can see that this has the triangle has 3 sides. right? But you have to multiply by 2 to get the 6 roots, because the roots can go both ways. And then you have to add the 2 diagonal guys, the lambda 3 and the lambda 8. This is the I plus or minus, U plus or minus, V plus or minus, and these are the isospin and hypercharge. So this becomes 8, and this is in fact 3 squared minus 1. So it works, okay? So now we make a guess what happens to SU4. Well, the things have to live in 3 dimensions. So I invite you to give a guess. You can guess in your mind what it could be, and see if you have any mathematical intuition. Well, from an equilateral triangle in 3 dimensions, obviously it's the tetrahedron. Okay, so if you guess it's tetrahedron, very good. Okay, so we'll just check that for the tetrahedron, this counting also works. So you see that there are 6 sides, 1, 2, 3, 4, 5, 6, 6 sides. So there are 12 root vectors, right? Because each side you can go both ways. And then there's 3 diagonal guys, 3 diagonal guys. So 15 is equal to 4 squared minus 1, which is exactly the number of generators. Now you see in this case, so if you are living in the late 19th century and early 20th century, if you were one of the following people, Catan, Killing, Lee, and so on, Sylvester perhaps also, maybe not Cayley, you would be very excited at this point that there seems to be a pattern. Now last time I wrote down a bunch of conjectures on the blackboard, and I asked you for your intuition to guess which ones are general, which ones are correct. Well, one of them was roots. All the roots have equal length. And I don't know how many people guessed that this would hold in general. Okay. Did most people guess this would hold in general or not hold? Okay, so here you see it works. The tetrahedron has all equal length. And then the other thing I wrote down was nice angles. The angles between the root vectors here are all 60 degrees and 120 degrees and so on. You don't get things like 19 degrees. Okay. So here, again, this works for the tetrahedron. You see all the angles are 60 degrees or 120 degrees. Okay. So both of these work. And now the next exercise is the obvious one. You can work out SU5 and see if the pattern continues. Okay, so now I'm actually, for the students who are reading the book, I'm now on chapter 6.2. in which I will work out the roots and weights. Roots, weights. For the algebra we know, which are orthogonal. For the groups we know in physics, unitary and symplectic. The symplectic I will explain later. So the orthogonal and unitary are known to everyone. Orthogonal just rotation, and unitary is in quantum mechanics, SU2 and so on. So given a Lie algebra, like for example SU2 or SU3, what do? We find the maximal set of mutually commuting generators. So this is, for example, SU4, the example I just worked out. They are lambda 3, lambda 8, and lambda 15. Okay. So this is how a mathematician would say, we find the maximal set, and in this case the maximal set is these three diagonal matrices. Well, what does the physicist say? Well, especially physicists like me who follow the sort of Feynman school, the physicists would just call this the diagonal guys. Well, at least in the US, maybe not in France. So these are the diagonal guys. And now we follow Cartan's notation. Cartan's notation is that these guys are called HI. Okay, it's obviously crazy to start to call them by lambda 3, lambda 8, lambda 15, and so on. In general, or for a general Lie algebra, this would be terrible notation. So Cartan calls it HI, I equal to 1 to L. And this number is called the rank. And so because when I wrote my book, I looked at various textbooks on group theory. And it seems that books, many in mathematics is always called L, but many physicist books, for example, books written by physicists, I think, for example, the book by Georgi and maybe the book by Hammermesh and so on, is often called L. So I try to decide between the two notation, but I finally decided I should follow Cartan. So I use L, okay? But just to tell you that, people. So let's just make sure everybody knows what L is. L equal to 1 for SU2, L equal to 2 for SU3, and so on, okay? So the rank is the dimension the root vectors live in. Okay. So here's our, I find an easy strategy. So this is an easy strategy. What we want to do is to work out the roots and the weights for these different algebras. And here's the easy strategy, is that first you find the HI, then you find the weight diagram of your favorite representation. Okay, so HI, so here's your favorite representation. So for example, for SU3, your favorite one would be the triangle, or the octet, this thing. So the proton and the neutron would be here if you want to identify with particles, and sigma plus, and so on. And this would be the up quark, down quark, and strange quark if you want to make contact with particle physics. But in general, you find the HI, and then you find the weight diagram of your favorite representation. So either the adjoint representation, the 8-dimension, or the defining representation. So I like to use the defining representation for obvious reasons. Defining representation. But mathematically, actually often, mathematicians often use the adjoint representation, as we will see. We will see later. This, of course, has the advantage of being fewer things. And then you join the dots. So this is like the children's game when you see many, many dots and so on. Okay. So join the dots to find the root vectors. Okay, so all the dots. If you join all the dots here, you see that the root vectors are then precisely this. The arrows that connect the 3 dots to each other are these 6 vectors, and those are the root vectors. So any questions? I hope this is clear. Okay. Now I'm going to do this strategy that I call the easy strategy. When I wrote my book, I looked at some books, and they make it some other books on group theory, and it seems very mysterious and complicated. And so I wanted to make clear that it's actually quite easy. You do this, okay? And certainly, when I was a student, I was quite confused. As I said, Coleman told me to spend the summer studying SU3, but now I realize SU3, I don't need the whole summer. One could do it in the afternoon. Okay, so let's do SU3 as an example, because we know SU3 so well. This is why I spend so much time on SU3. So the first part of the strategy is to write down the H. So H1 is the diagonal, and this notation means the diagonal matrix with these diagonal elements. 1, minus 1, 0. And there's some normalization factor, which I'm not going to worry about too much. Then H2 is diagonal 1, 1, minus 2 over root 6. Okay. Now, you notice already that this normalization is different from the physicist normalization. So this is mathematician normalization. So these are trivial things, but it's just very annoying, especially when you're writing a book. But if you're not writing a book, you don't have to worry about the normalization, because you should get it correctly. You can see that it differs from, because Pauli fixed the normalization by writing down sigma 3, so physicists use that. But mathematicians use this. And that's because they don't know anything. They don't care about Pauli. They follow Cartan. So this is the normalization that mathematicians use, which is trace of Hi Hj is delta Ij. So trace of this matrix square is 1, and trace of this square of this matrix is 1. So you can see the. So this is trivial, but that's life, okay? If you want to go between physics and mathematics. Okay. Now you want to find, so we now say that the weights live in a two-dimensional space, and one axis is H1, the eigenvalue of H1, the other is the eigenvalue of H2. So this notation means, let me put quotation mark. I don't mean to put the matrix on the coordinates on the axis. It just means you classify them according to the eigenvalues of the. So the three states of the defining representation. So I use this, as I said, I'll use this. This is the second step. We have to find the coordinates of these three things. Well, as you can see, that's really easy, because all you have to do now is to just circle the things vertically. So the first weight is just, well, let me circle them first, just this, right? So the first weight is 1 over root 3 over root 2, W2 is minus 1 over root 3, root 2, and W3 is 0 minus 2 over root 3 over root 2. So it's just the equilateral triangle again. So you see what do you understand what I'm doing? I'm just copying this 0 minus 2, but with the normalization. Yes?
Why does it work?
Sorry?
Why does it work?
No, by definition, the defining representation, it's locating where the up quark is in isospin and hypercharge space. So this is isospin, and this is hypercharge, suitably normalized. So by definition, the diagonal elements are the eigenvalues of isospin and of hypercharge. So it's by definition. So this is the isospin and hypercharge of the up quark. This is the isospin and hypercharge of the down quark. And this is isospin and hypercharge of the strange quark. The strange quark, by definition, is 0 isospin. Yeah, question?
How would you do this differently if you chose the joint representation?
Oh, then the H1 would be, there will be 8 numbers. And then you have 8 columns. Yeah. So clearly, it would be very, you cause trouble for yourself if you pick the 27. You know, as Feynman said, you know, throw away the 27. If you choose to work with the 27, it will still work. But then it would have 27 numbers, right, with 27 states, and there will be 27 of these blue circles. The matrices will be 27 by 27. It will be diagonal. Okay, you can do it, but it would be maybe in spite of Feynman, one should give an exercise and make students work out the 27 in its full glory. I've never seen the 27 worked out, I guess ever since what Feynman said. All the students avoid 27. Okay, any questions? Okay, then the next step is to join the dots to find the root vectors. Okay, so of course we're not children, so we don't have to join the dots. We know how to do this. We just subtract vectors, right? This arrow is just this coordinate minus that coordinate. So just subtract. So the root vectors, the third step is root vectors. Okay, root vectors. Now, because I'm writing this on the blackboard, and in the book also, when I was teching all this, at some point I get tired, right? So no more arrows. The vectors are not going to have any arrows on them from now on. Okay? So the first root vector, and again, this is mathematician notation. The root vector is alpha 1. The first one is W1 minus W2. And this is square root of 2, 1, 0. Alpha 2 is W2 minus W3 is equal to minus 1 over root 3 divided by root 2. And alpha 3 is equal to W1 minus W3. These are 3 of them. And then the other 3 are just the negative and their negatives. So we see that this is I plus. So this is I've forgotten whether it's U plus or V plus. And this one is this guy. And then, of course, you have their negatives, the thing pointing in the other direction. So those are the 6 root vectors. Okay. Any questions? So I think you can, by now you can mechanize this, and I'm sure some students will now write a computer program, a mathematical program in which you can press a button and produce all the roots of any Lie algebra you want. Okay. Now, last time I introduced 2 important concepts. One is positive roots, and the other is simple roots. You remember I introduced these 2 concepts, which are called positive. And now I'm going to follow the mathematician's convention. So you see that the physicist convention was that they favor isospin over hypercharge, just for historical reasons, because Heisenberg is a big guy, and he had isospin first. But the mathematicians favor H2 over H1. So as I said, which you call positive of the 8 root vectors here, doesn't matter. Physicists are mostly pointing east, and mathematicians mostly pointing north. Okay, so but with this convention, then the positive roots are Wm minus Wn with m less than n. These are positive. And what are the simple ones? The simple ones, if I use the mathematician's convention, they are clearly these 2. And so it's W1 minus W2, W2 minus W3. So first you find the positive roots, and remember the simple roots are the positive ones in terms of which the other positive root can be written with positive coefficients. That's very, see, this is a confusing way of saying things, but it's trivial. It's sort of the outer. Yes, please.
I think that you made a typo for lambda 3.
Yeah?
The arrow is wrong.
Yeah, that may be, yeah. This one.
Yes.
Yeah, thank you.
It's positive.
Oh, this one, yeah. Okay, thank you. Yeah. Okay. Yes, oh, Kiron.
Yeah. You consider that the top-down matrices are given.
Yes,
Do they have a-
that you have to find them.
how do you
Yeah.
find them?
Yeah, that's a good question. I think a physicist would just write down all the diagonal ones.
If I give you an abstract answer,
Yeah, abstract algebra, you have to solve this some eigenvalue equation, which you probably know, right? Yeah. Okay, but it's a good question. So I should announce to all the students, Kiron just asked a very good question. And if you want to know the answer, you should ask him. You know, how to determine the catastrophe algebra. Yeah, no, it's a good question. Okay, so I hope that this is clear, and the students should then go on to work on SUN, to write down the root vectors for SUN. Okay, so it's completely just like this, except that it gets to be very tedious, because with these normalizations, there will be, for general SUN, as you can imagine, there will be many square roots of n times n plus 1, and so on and so forth. There will be, okay. So pedagogically, it's actually clearer if we do the SO groups, okay? So, and I also want to do something different, because we have spent a lot of time on SU3. Let's do the SO groups, okay? So is that, any other questions? I don't know if I'm going too fast or too slow for the students. Okay. So as I said, we'll now move to the SO groups for a while. Now, one interesting thing is that physicists learn the SO groups first, because obviously orthogonal, and these people that do financial random matrices, they don't care about unitary stuff at all. They don't have complex stock prices. So physicists are always learn the orthogonals first, and then move on to unitary. So in the history of physics, unitary matrices seems more advanced. But actually, mathematically, the orthogonal matrices, as you will see, are in some sense more complicated, because the orthogonal matrices, the orthogonal groups also have have spinor representations and so on and so forth, and they will have features that you would see makes things quite different, quite interesting. Well, the first one, the first non-trivial one, is just locally the algebra is isomorphic to SU2. So the next one is SO4, which is important in physics because the analytic continuation is the Lorentz group. Okay, so it's the generators. This is antisymmetric, classified by antisymmetric tensors. Okay, so the diagonal guys are J12, J34, and J12 are the rotation in the 1-3 plane, and this is rotation in the 3-4 plane. So in physics, of course, with some analytic continuation, as Minkowski pointed out, 4 is time. Okay, the 1, 2, 3. So this is the rotation. Oh, I'm sorry. I said I have a typo. 1-2 plane. And of course, for physicists, this is rotation around the z-axis. And this is a boost along the z-axis. Okay? But in general, the rotation should be written this way. So these are the two diagonal matrices. So you write down 4 by 4 real anti-symmetric. So the generators, of course, real anti-symmetric matrices with an I. Well, I'm not going to worry about the I, but the rotation matrices. So this is the H1 is just 1 minus 1, 0, 0. So the usual of rotation matrices around the z-axis would be 1 minus 1, 0, the 3 by 3. But we are in 4 dimensions, so it's 1 minus 1, 0, 0. And the other one is obviously 0, 0, 1, minus 1. Okay. So now you see we mechanize this procedure. We've written the students have written a computer program, and we can do this. We can find the weights right away. So the weights, you just go like this. So the 4 weights are W1 equal to 1, 0. W2 is minus 1, 0. Okay, W3 is 0, 1. W4 is 0, minus 1. Okay. So the weights are them, and this guy, this guy, this guy, this guy. Okay? So this is kind of very, we feel good, because after the equilateral triangle, we meet our old friend, the square. So this is our, when we're children, we learn the triangle, and then we learn about the square. So the square appears. And now we find the roots. The roots are just the things that connect these guys, right? But both ways. The roots. So the roots, alpha 1, for example, is W1 minus W4, which is 1, 1. And I would not write them down for you. You can write them down. And so the roots are just, the root diagrams is just this. Very nice, right? So let's check. There are 4 roots. Okay. There are only 2 positive roots and 2 negative roots. And plus the 2 diagonal guys. 2 diagonal guys, it's equal to 6. But 6 is rotation, 3 rotations plus 3 boosts, to use physics language, or to use mathematics language. It's 4 times 4 minus 1 divided by 2, which is 6. Right? The anti-symmetric rotation. Okay. Yeah.
In the previous case, we had 3 roots and a negatives. Why did we not take the negatives now?
Oh, we did take the negatives. We have 2 roots, 2 positive roots, and these are the negative guys. Okay, the 2 positive roots are these 2. And they are the negatives. But good question. Okay. All right. So now I've even better question for, I have a question for students. I have the answer written here, but to save time, I see I'm already 45 minutes into the lecture, is that this is a question for students to think about. I only connected, when I connected these 4 weights, I don't have a root that takes this guy to this guy. Why? So you have to think about it. The answer is clear. There's not going to be a there's no rotation which takes this into that. Okay. Now you can see an interesting fact from this root diagram. You see that last time we say the commuting, remember that when we did the I spin and U spin and so on, we add the root vectors to find. So for example, if we commute this with that, we find we add the root vectors to find another root vector. And if this root vector doesn't exist, then the commutator must be 0. Okay. And if it exists, it's there. Now here, see, it's interesting. If I take this generators of this rotation, this root vector, and I add it to this root vector, then I get this root vector, right? But this root vector doesn't exist. So these two things must commute. So this shows that the generators of this and this commutes. So in fact, you can see that the SO4 from the root vector, you can see it's isomorphic to SU2 to SU2, cross SU2, the SO4. Okay. Okay. So it's two separate SU2 that are given here. Okay. Now you can so now in also notation. We'll define unit vectors E1 equal to 1 comma 0, E2 as 0 comma 1. Okay, so those are the obvious, just the unit vectors. The unit vector in this space. Then you see the positive roots. We define the positive roots. The four roots are the plus or minus E1 plus or minus E2, in which the signs are uncorrelated. So you can choose in all possible ways. Those corresponds to these four vectors. And the positive ones, the two positive ones, are E1 plus or minus E2, and they're both simple. Okay, so that's SO4. I start with SO4 because SO4 is an example that we know very well, and it's also an algebra that's very important in physics, especially in relativistic physics. So the analytic continuation of this is, of course, the Lorentz algebra, which is ESCO chemistry 1. And the fact that it has two isomorphic SU2 is, of course, what leads to the Dirac equation. Okay, so that follows, Dirac equation follows basically in one line from this. You can look at my group theory book if you're not familiar with this. Basically, the two directions are the two Weyl equations. So Hermann Weyl wrote down equation for one and for the other. But Hermann Weyl's equation was rejected by physicists because it was not parity conserving. So Dirac's work, in hindsight at least, is putting the two Weyl equation together. Now, of course, historically, this is a classic example of physicists not knowing any mathematics, but able to get ahead. Dirac did not know anything about group theory or the algebra. He simply guessed the equation. Okay. So next, I show you something interesting. So which is SO5. Now we move on from SO4 to SO5. There will be some surprises. So SO5, the diagonal guys are H1 and H2. The diagonal is 1 minus 1, 0, 0, 0. Okay. And diagonal 0, 0, 1, minus 1, and 0. So these two are, of course, exactly the same as SO4, which is, of course, a subalgebra of SO5. But now it's, of course, 5 by 5 matrix. So there's an extra 0 at the end. Okay. So H1 and H2, well, find another. So this is the first surprise. So find another, and there's none. There are no other diagonal matrices you can find that are traceless. Okay. So this is an example. This simple example answers, but only very partially by example, of Quiron's question. Quiron's question was, how do you find all the H's? Well, physicists write down the diagonal matrices and they cannot find another one, and so they said the only two. The mathematician will have to prove this, okay? But I think it's clear to Feynman and Landau and people like that there are only two, okay? Somehow these people don't need proofs. So we see this is very interesting that although SO5 is bigger than SO4, right? SO5, I should write it like this. SO5, SO4 belongs to SO5, but they're the same rank. They both still rank 2 algebras. So this is, make a very, very slight joke. This is somewhat different from human society. One guy is bigger than the other, and the other guy is just a subset of him, but they have the same rank still. Okay. So, but then there's one more weight, right? In fact, let me be consistent and use the same color. So here I have 4 weights, and now here I have one more weight. W5 is equal to 0, 0. Okay? So now so the weight diagram is now we have the guy in the middle. 0, 0. So compare and contrast these two. So interesting, when you go from one SO group to the other, you've acquired the thing in the middle. Okay. Now about the roots. By the way, okay, so there's one in the middle. So now the roots, we have these guys, but now we can also have roots that take this guy to this guy, right? These are all roots now, and the negatives. So now the root diagram suddenly becomes this. Sorry, it's the same diagram as before. This one. Right? This one with these 4, but then we now add these. So that's the root diagram. And the new feature, so you see there's a new feature here. I asked you to conjecture all kinds of things last time to test your mathematical intuition. And one of them is all the roots are of equal length. That was a conjecture. See? If you guess it was correct, you guessed wrong. Your intuition was wrong. This is the first example in which you have roots with different lengths. Okay? So there are 4 roots whose lengths are square root of 2. In some, if we normalize this to have root 1, then there are 4, and the mathematical notation, mathematicians call them long roots and short roots. So now we have a new concept, long roots and short roots. There are 4 long roots and 4 short roots. Okay. So I think I don't know how many people have correct intuition. But the angle business is still correct. It's a nice angle. It's 45 degrees. It's not 44 degrees. It's not 46 degrees. Okay. So. Yes.
Claim that 90 degrees is bad.
90 degrees means that.
45 was good.
Yeah, 90 degrees is not bad angle. It just means the 2 algebra decouples. 90 degrees. But as you see, you would see later in Catan's classification, 90 degrees is also a special case. So this is, of course, going to be Catan's strategy, the classification strategy, that to prove that only some angles are possible. So again, this is something for the students, a challenge for the students. You can try to prove it now. because looks like I won't be able, I don't know, I probably won't be able to prove it today. So here's the challenge for the students. Prove that the angles between the roots cannot be 19 degrees or 47 degrees, but it has to be a nice, quote-unquote, nice angle. Of course, the concept of nice is not defined for a mathematician, but physicists know what nice means. So physicists knows that 20 degrees is not nice, but 30 degrees is nice. How's that? Okay. So now we can again write down all the roots. So I would just write here. So is this clear? So there are 8 roots, and using the same notation and signs, I would just write uncorrelated as UNC. So then it's just like here. The roots are, the signs are uncorrelated. So the 8 roots are plus or minus E1, E2, and then E1, plus or minus E1 plus or minus E2. We have 4 extra short roots. So the long roots and the short roots are going to be, they will have different. And by the way, so that's this already tells you about the Dinkin diagram. If you've ever seen a Dinkin diagram, you see it consists of circles and lines, and some circles are black and some circles are white. And so this is a preview. The long roots are black and the short roots are white, or vice versa, depending on your convention. So positive roots. So what are the positive roots? Is E1 plus or minus E2, E1, E2. These are the positive roots. So these are exercise for you to work out. Simple root, the positive roots are obvious, but the simple roots is the exercise to work out the simple roots. And it's E1 minus E2 and E2. Now at first sight, so that of course there should only be 2 simple roots because it's the algebra is rank 2 and the roots live in 2-dimensional space. So this at first sight this looks very strange to a physicist because physicists believe in democracy of some kind. So it may look strange that only E2 appears and not E1. But that's, of course, when you define positive roots and simple roots, you already favor one axis over the other. Okay, so it's not democratic at all. Okay, so work out that this is are the 2 simple roots. So to prove that, the exercise is just to show that E1 is not simple. Right? So this you can almost do in your head. And I think Kiron is doing it in his head right now. I can see his expression on his face. I can almost see the wheels in his head turning. Okay? So good. Okay, now in fact this gives me an opportunity to give a lot of exercises. Obviously I don't have time to work all these things out on the board. So again, these exercises are rather fun. So one is obviously work out SO6, and another exercise is you can see that SO2L versus SO2L plus 1, you can already see they're different from this example, SO4 and SO5. And in fact, it's interesting because mathematicians think of them as 2 distinct families, 2 distinct infinite families. Okay? And the other exercise I already gave, which is to work out SU4, to see that the tetrahedron emerges. Okay. So this is interesting because physicists know about the unitary groups, the orthogonal groups, and the symplectic groups. So then physicists know of 3 families. But you know the mathematicians somehow have 4 families. And the reason is because their notations often are not terribly imaginative, less so than physicists. Their notation for is ABCD. And that's why the exceptional algebras are E and F. So physicists, maybe you should be puzzled why we have orthogonal, unitary, and symplectic, and they have ABCD. And it's because the 2 SO, what physicists think of as the odd orthogonal groups and the even orthogonal groups are different mathematically. They're the B's and the C's. Okay. So I'm going to now just start on the symplectic groups before the intermission. So the symplectic group, I'm going to tell you an algebra. I will tell you a story later. It's rather unfamiliar to physicists, so I need to go back. So I'm just going to define the symplectic algebra, and I'll ask the students to read chapter 4.8. So today's lecture is actually chapter 7 point something. So this is in the first half of the book. There's a chapter on symplectic. Okay, so talk about the symplectic groups. You first have to define a matrix J, which is 2n by 2n, in which you put the identity matrix here and minus the identity matrix there. Okay, so J is an antisymmetric matrix. And so let's see the 2n by 2n complex matrices. So complex means that the elements are complex numbers such that CT J C is equal to J. So that J is invariant under C. Okay? And this defines the group SP 2nC, symplectic group on 2n and C. Now, when students first see this, they immediately wonder whether this is a misprint. It's T and not Hermitian conjugate, because C is complex. So this is not a misprint. It really is T, the transpose. Certainly, when I was a student, when I first saw this, I thought it was a misprint also. But it is, in fact, not a misprint. It really is T and not adjoint. Okay. Okay. So now the next step is so this defines a group. But now you add another restriction. You require C. So first the exercise for the students during the intermission is to check that this is a group and so on. It satisfies all the definition of a group and so on and so forth. With the transpose. Okay. Now the next step is require C to be an element of U2n, to be a unitary matrix. Now, remember it's 2n, not n, because it's 2n by 2n matrices, okay? So now we call C U. So that is to say we also write U, J, U equal to J. So that is to say unitary matrices that satisfy this. So the claim is unitary matrices that satisfy this condition defines a group. And you can check that it is in fact a group. So this group is called USP 2n. Now here's a warning. Some physicists are very sloppy and they confuse USP with SP. So I can tell you, there are books written by physicists in which there's no distinction between USP and SP. This has led to a lot of confusion because in the more mathematical literature, of course, we can also define SP2n now. So that's defined on the real matrices. So I define C, but this I won't even mention here, SP2n now. It's a subgroup. So mathematically, and you can write this, of course, the definition of USP2n is U2n intersection with SP2nC. It's the intersection between these two groups. Okay. Now here's an exercise to show that it is not, this USP2n is not subgroup of U2n. And the solution is very easy. You can do it in your head to show that it's not a subgroup of U2n. And after intermission, I would give the solution. But so as a challenge during intermission, you can solve this simple exercise. It's a one-line solution. You can figure it out in 2 minutes. Okay, so we'll stop here and come back in 10 minutes. Okay, begin again. So I realize students are full of questions, which is a good thing. So some students came and asked me questions during intermission, and I realized that many of the questions are points that I have explained in great detail, but in the first half of the book. So because this course sort of jumped in the middle somewhere. So one student asked me the difference between the defining representation, the adjoint representation. So one way to think about it is just for SU2. So the defining representation is obviously two-dimension. That's the definition of SU2. You transform two things. But the generators of SU2, because it's rotation, so the rotation group has three generators, J1, J2, and J3. And that's the adjoint representation. The adjoint is three-dimension. The three generators form a representation, okay? So just like in SU3, the defining representation is three-dimensional, but the adjoint representation is eight-dimensional because there are 8 generators. So I don't remember the chapter, but in, I think, one of the early chapters on rotation, I discussed the adjoint representation in great detail. So if you have the book, you should go back and look at one of these early chapters. By the way, my pedagogical style is I like to take a simple example and beat it to death. It's called beating it to death. So I take something like the rotation group and I put down everything I can think of about the rotation group. So it's just exhaustive and exhausting discussion of rotation. So the adjoint was defined in connection with that. Now the other question was that J mu nu, I wrote down J mu nu as the generators, and that's also very confusing to people, but this point is also discussed in the chapter on rotation. The reason for that, why the generators of rotation have two indices, it's a very interesting point actually. Because from childhood, we think about rotation around some axis. So I see some people smiling in the back, so these are the more advanced students who know what I'm going to say. So we talk about Jx, Jy, Jz. Jx is the rotation around the x-axis. And so, or J1, J2, J3. But you can see that this does not generalize to higher dimensions. Suppose you're in 27 dimension. What is J27 or J20, J17? There's no such thing as rotation around the 17 axis. But instead, there's a rotation in J1720. So J17 comma 20, which is the rotation that rotates the 17th axis into the 20th axis. Okay? And the reason it's anti-symmetric is J1720 and J2017 are opposite rotations. One rotation turns the 17th axis into the 20th, and the other turns the 20th into the 17th. So it's very special for 3-dimension, and we live in 3-dimensional space, that you can talk about rotation around an axis. And because only in 3-dimension, a plane is dual to an axis. In any given plane, there's a axis perpendicular to it. So an axis specifies the plane. It is one-to-one identification. But it's not true in higher dimension. Even in 4-dimension, you cannot talk about rotation around some axis. I hope that helps the students. But for the more elementary students who are I can see how these questions are bothersome. But unfortunately, I wrote this huge book. But obviously, I cannot start with page 1 here. So in Santa Barbara, I start with page 1. And then we never get to Cartan classification. So the reason I offered to give Cartan classification here is because in Santa Barbara, I never got to Cartan classification. So I probably should stop talking, because otherwise I would not get to Cartan classification. So I better hurry up and... Okay. So I assigned a exercise before intermission, and I asked people to prove this, that USP2N is not a subgroup of U2N. Okay? So here's the solution. I hope that many students solved it already. So yes or no? I mean, people have solved it. Here's the solution. The solution, to show that it's not a subgroup, all you have to do is to find an element of U2N which is not in USP2N. That's all. Okay? So it's e to the I phi times the 2n by 2n identity matrix, just identity. Well, you can see it does not satisfy this. Okay? So is that clear? So that's also a point of confusion. People think somehow it's a subgroup of U2N. It's not. Okay. Yeah.
What exactly did we prove?
That USP2N is not a subgroup of U2N. That group.
Find an element in USP2N which...
Right. Which is not an. Is that clear?
Sorry, not quite. This is an element of U2N, right?
Right.
But this is not an element of the USP2N.
Right. Because it doesn't satisfy this equation.
But this is completely fine for a subgroup, right? There are elements in the group, in the total group,
Yeah.
that not belong to the subgroup.
Right. So it's a subset.
Yeah.
It's an intersection between these two groups. Yeah. Okay.
So, yeah.
Yeah.
So this is fine. There are some elements which do not belong to U2N.
Yeah, yeah, sure. Of course, it's fine. There's no contradiction. Yeah.
For subgroup, but
Yeah.
why does it? Okay, yeah. If it's clear to everyone, then okay.
Okay. All right. We'll talk about this later. So, maybe you can ask Kiron what I meant. Kiron would explain it. Yeah. Maybe I said something wrong. It's possible.
You meant that it's not identical USPN to
UN. Yeah.
That's for sure.
That's for
Still
sure.
there is it,
Yeah.
But if it's still the subgroup.
It's a subgroup. Yeah. Okay. Yeah, I said something wrong. Okay. So let me not worry about this at this point. So I want to move on. Okay. So the exercise that I want people to do, another exercise, is for this group. It has n to n plus 1. Show that it has this many parameters. Okay? USP2n. Okay. And so the next step is to go to the Lie algebra. So far we have talked about the group. So the Lie algebra is, as I explained in an earlier chapter, is you just look at the infinitesimal group elements near the identity. So H is Hermitian, and because I said something wrong, in fact, because it's an intersection of U2n, and so it's inside U2n, this thing. So H has to be Hermitian, because this is in U2n. Okay, so it's I plus IH transpose J, I plus IH J. And so this is HT trans J equal to minus JH. And now, since we use the fact use J squared is equal to minus 1, you multiply J on the right-hand side, you get HT is JHJ. So J turns a Hermitian matrix into its transpose, like this. But this is not a similarity transformation. J is not the inverse of J, because J squared is minus 1. Okay? So again, these look very strange, because usually you think of Hermitian matrices, you think of Hermitian conjugate. Okay. So now we can use this to solve for the Lie algebra, which I'll give an exercise, is to find the algebra. Okay? So this you do by saying H is, you write down the most general, this is sort of the physicist's way. I don't know, mathematicians maybe have. So this is just the poor man's way. You write down 2n by 2n Hermitian matrices. 2n. So this means P and Q are n by n Hermitian matrices. And W is in general complex. So this is W and W dagger, okay, not Hermitian. So write down this thing, and you plug into this equation and plug in and show that what PWWQ must satisfy. And after you do this, you find what the possible H's are. It's IA, direct product with I, okay? So this is 2 by 2. Okay, and I'll tell you what the notation means. S1 cross sigma 1. S2, the Pauli matrices appear again. So these are symmetric n by n. S1, S2, S3 is 3 arbitrary, they're completely arbitrary Hermitian. And this is anti-symmetric n by n matrix. So you can check that the number of possible linear independent matrices corresponds to this number. Okay. Now, okay, is that clear? You plug in this form into this equation and solve, and then you find constraints on P, Q, W, and so on, and then you find that the solution is this. Okay? So for example, this guy in my notation would be S1, S1, 0, 0. Okay? Now here's the more exercises, which is not surprisingly some of the so also sloppy physicists notation, sloppy physicists. They often, instead of USP2n, they just write SP2n. The U is dropped in the physics literature. So this caused me a lot of grief when I was writing my book, because some people state some results and then I was not able to derive them and so on. But anyway, now using this sloppy physicist notation, it would not surprise you that some of the symplectic, low-lying symplectic algebras are isomorphic. Well, SP2, for example, SP2 it corresponds to n equal to 1. And according to that, the previous exercise, it's 1 times 3 has 3 generators. Well, we know there are not so many algebras with 3 generators, right? You know, you write down 3 things, A, B, C, and you start commuting them to form the algebras. You soon discover there's only basically 1 possibility. So, not surprisingly, it's isomorphic to SU2. Now here's the one that is more surprising, which is the symplectic group SP4 is isomorphic to SO5. And a trivial check is, of course, generators, and so here you find that 2 times 2 times 2 plus 1 is 10, and 10 is exactly 5 minus 1 over 2. By the way, you can see in that group theory obviously has a lot of connection with number theory because various identities must work. So all kinds of weird things like this. Okay, so I promised to tell one student during intermission asked me, told me that students here have not studied symplectic groups at all. And certainly when I was a student, I think I don't think I even heard of the symplectic group. I think maybe in an advanced course on mechanics, Hamiltonian mechanics, P and Q, the professor might mention that P and Q form some symplectic structure or something. So symplectic group, I don't know. Very few people know about it. So in George I's book, he dismissed the symplectic algebras in basically 1 or 2 pages, and he said something like it's irrelevant for physics, so forget about symplectic algebra. So here's the story. A few years ago, some string theorists went to Harvard to give a talk, and in the entire talk he talked about symplectic algebras. And in the end of the talk on his PowerPoint, he showed a quote from George I saying symplectic algebra is irrelevant for physics. And then he said, look at this quote. And Howard George I jumped up and he said, your work proved my point beautifully. So the person and the entire audience laughed just like your reaction, and this guy was really put on the spot. And the person who told me, I was not there, but somebody told me this story when he was visiting Santa Barbara. And he said that poor guy was really asking for it. So the American expression for that is like in a baseball game, if you throw a really soft pitch to the batter. And okay, so he was, and knowing George I's personality, he was indeed asking for it because George I often likes to insult people and so on and so forth. So, who knows, maybe in the future symplectic algebras would become important, but so far I don't know of any real examples. I've seen some work on nonlinear dynamics in which people use symplectic differential equations that have some symplectic structure, but nothing like the unitary groups and orthogonal groups, which are really essential to physics. Okay. So now we go back to our lecture. So this was a very quick introduction to symplectic algebras, right? So this is very, very quick. And now we want to go back to Cartan's classification and the roots. So there is this group that seems very natural, but somehow nature doesn't seem to use it very much. So now we can figure out, just go back to mathematics, we can figure out the roots and so on using our strategy. Now, what are the HIs? What are the HIs for the symplectic algebra? And you can see that the HIs are actually, in the American expression, would be handed to us on a silver plate. Okay? So it's literally handed to us here. Okay? Because the HI are just these guys, in which the S3 is diagonal. So it's like this, in which you have 0, 0 and then a 1, and then 0, 0, 0, 1, 0, 0. This is all 0, 0, 0, 0, 0. Okay. So I don't know what we would do if the Indians never invented 0. So these are the HIs, and you can invent a notation. It's UI, little ui cross S3. I'm sorry, it has to be -1. I forgot, and it's cross S3, so minus. So is that clear? Where UI is the diagonal matrix that's all 0 except with a 1 in the ith position. Is that clear? Right? So it's that this set of matrices, they are the HIs. Okay. So now I can write down the general, since I have the HIs, I can follow the strategy I outlined earlier and work out the roots and so on and everything. But since time is short, I'll leave that as an exercise. I would work out only SP4. Now, in fact, in working out SP4, we're going to discover this interesting isomorphism, okay? Which seems very strange. But because the whole discussion doesn't seem to have anything to do with rotation, and suddenly the five-dimensional rotation appears. So SP4 has 2n is equal to 2, right? Because this 4 is 2n. So H1. By the way, when I was writing my book, this also drove me crazy because I looked at different textbooks, and some people define 2n as n, and some so H1 is 1, 0, minus 1, 0, according to this. H2 is diagonal guy, 0, 1, 0, minus 1. So, using our method, we can immediately write down the weights. The weights are these 4 guys. So W1 is 1, 0. W2 is 0, 1. And W3 is minus 1, 0. And W4 is 0, minus 1. Okay? And it's these 4 roots. So the weight diagram, you see, the weight diagram for SP4 is exactly the same as SO4. But of course, it's not the same, but not really the same. Not really the same. Because as we see, SO4 only has 6 generators, and SP4 has 10 generators. So there are 4 more roots. SP4 has 4 more roots than SO4. Okay? Because before we can only have these guys taking the 4 things, and now just like before we can have these. So again, I hope I have not erased it. Aha, here. So the root, so it's exactly this, and the root diagram is the same as SO5. So you see SP4 is the same as SO5. So by the way, if you try to prove the isomorphism by brute force, it takes a little bit of labor. But you can also, as an exercise, try to prove it by brute force. Yeah, question, please.
You don't have the weight on 0, 0, so you have to switch between the long roots and short roots.
Yeah, very good. This is maybe what I'm going to do next. Let me see if I answer the question. Okay? So now if you look at the root diagrams, I think this is a very good question. I think I have the answer. I'm not sure. But now you find that the roots are EI plus or minus EJ and plus or minus EI. plus or minus. The signs are not correlated. So now the roots, if you work it out for SP4, we see that it is this. So this is exactly the same as this, but rotated by 45 degrees. So the long roots and the short roots are rotated, okay? But the structure is the same. Does that answer your question? Yeah. Yeah. Right. Right. Yeah. You have to. So the two things are rotated by 45 degrees. Okay. Okay, so this is very concrete, this lecture so far. It's what physicists would do, write down explicit matrices and so on and so forth. But now I move on to the mathematician's classification. And so now I'm talking about chapter 7.3 in the book. And this is Lie algebra in general. So how do you write down a general Lie algebra? Okay. So first we're talking only here about compact Lie groups. So for example, not the Lorentz group, because boos are infinite. By the way, so for those of students who don't know about compact versus non-compact, this is discussed in great detail in the first half of the book, on which I also talk about integration over group manifolds. So it's whether the integral over the group manifold is finite or not finite. Okay. So there's also a theorem which I also talk about in the beginning of the group, in the book, first half of the book. Compact groups have unitary representations. Since the representations are unitary, that means the generators are represented by Hermitian matrices, which is what we have all along. Okay, so these are just to remind you of these three facts. And now mathematicians define very abstractly and generally a Lie algebra. So Lie algebra is just a set of n objects, the index ABC goes from 1 to n. And these objects xa are called generators. And n is the number of generators. And they satisfy this commutation relation. So that's the definition of a Lie algebra. And now, for the first time, I now have upper index and lower index. And so you will see later that in mathematicians also define a metric. We will see very quickly that there's a metric. So it's using the metric to lower and lower and raise indices. So this also means, so you notice that two of these guys are upper index and this is a lower index. And so again, we now have Einstein summation convention. That repeated indices are summed over, and also that the rule is that you always sum lower index with upper index. Okay. Any questions about this? Okay. Now, since X are represented by Hermitian matrices, X are Hermitian. So as I said, physicists are very sloppy. Mathematicians think of X as an abstract object, but physicists already immediately think of representation. They can just think of the matrices representing the abstract object. So since X is Hermitian, this implies that FABC are real numbers. So just a bunch of numbers. So these are called structure constants of the Lie algebra. So they specify the Lie algebra. So each Lie algebra is specified by these FABC. And so you know what the FABCs are, for example, for SO3 and SU2. The FABCs are just the Levi-Civitas symbols. Civitas symbols, right? Okay. So any questions? So during intermission, a student asked me about the adjoint representation. So the adjoint representation is going to come in shortly. So far we don't know a representation of the Lie algebra. But it turns out that the structure constants themselves define the representation. And this representation is called the adjoint representation. So for SO3, SO3 is the example. The structure constant is just epsilon ABC, the Levi-Civitas symbol, and epsilon ABC defines the 3x3 rotation matrices, the generators of 3x3 rotation matrices. Okay? Oops. I guess I should push this up first. So I think I'll erase all the symplectic stuff. Okay, so what can we do, Mr. Jacobi? So Jacobi identity, I assume all the students know about Jacobi identities. If you have three objects A, B, C, the commutative A, B with C plus the cyclic permutations vanish. So this is, if you don't know it, you should prove it. It's a very important identity in physics. For example, Einstein gravity would not be possible without Jacobi identity. So plus the two cyclic permutations. So I won't write down the terms, so that just cyclic means A becomes B, B becomes C, C becomes A. There are two other terms. So plus B, C, A, C, A, B. Okay? It's three terms, and it adds up to be equal to 0. Okay? Now, if we commute this, this obviously is FABD, XD, and then we commute with XC, right, this term. And XD with XC is FDCG XG. And so all three terms can be written as plus the other stuff equal to 0. So we can group all the terms, and it's the coefficient of xg equal to 0. And so this guy must be 0. So this guy is FABD, FDCG, plus two cyclic permutation. Okay? So all the indices and so on worked out in my book. So when I guess in the old days it must be terrible for Catan and these people to write these things. But nowadays, of course, you can just copy and paste and make the computer cyclically permute the indices. So is this clear? This is a D. The D is summed over, but A, B, C and G are free. So there's an identity. The Jacobi identity says the product of two structure constants satisfy this. Okay? Okay. So I make a historical remark here for people who are old enough. So in the old days, a long time ago, people like Landau and others claimed that quantum field theory was dead, and particle physicists should stop learning quantum field theory. And in the United States, it's a big enough country, so on the East Coast, people learn quantum field theory. On the West Coast, people do not learn quantum field theory. And so then if you were, as I was, going to graduate school, there was a choice between, I had a choice between going to East Coast or to West Coast, and that the deciding factor is whether you want to learn quantum field theory or not learn quantum field theory. So if you go to the West Coast, like Berkeley and Caltech, you learn about bootstrap. And bootstrap says the world is not described by quantum field theory, but described by some self-consistent equation. And again, the name, I think, was invented by Gelman. You pull yourself up by the bootstrap. And so these are the self-consistency equations. This is on which all physics was supposed to be based. So fortunately, that turned out to be wrong. And so the people that learn quantum field theory all the people that went to the West Coast have to quickly learn quantum field theory on their own. If they're smart enough, like David Gross, who went to Berkeley, he quickly learned quantum field theory. But people who were not, they were lost. So anyway, that's a historical remark. So now, what we're going to do is going to define n by n matrices. Now this seems very strange, and this is, you have to be careful. The n of them, each one of them is n by n, okay? And these matrices are going to be called TA, okay? A equal to 1 to n. And in the United States, TA means teaching assistants. So there's always some teaching assistants hanging around. So, and the definition is that TA, this matrix TA, its entry, it's BD entry, so it's the entry in the Bth row. So let's see, is it row or column? It's the BD entry. So B is the row and D is the column, right, or something. So, but let me just call it BD entry is equal to, defined to be minus F ABD. Okay? So is that clear? So everything is n by n. ABC runs over n, ABD run over n by n values. But A is now labeling the matrix. It tells you which matrix you're talking about. And then B and D tells you which row and which column. And it's given by the structure constant. Now, it's good to think of the SO3 example. In SO3, the F is just the antisymmetric Levi-Civita symbol. So for SO3, these three matrices are just 1 minus 1. There's a minus I. So the I has to be included. You know, just the three rotation matrices that you learn when you learn about rotation. Okay? So those are the three matrices for SO3. But in general, for a Lie algebra, there will be n such matrices made of the structure constant. Okay? Now, we take this equation, and we have to massage this equation. And after some massaging, you would discover that it tells you something very nice. Okay. For example, this first term, you can see FABD is just the matrix TABD times the matrix TC DG. up to some sign, okay? So up to some sign and minus i's and so on, okay? And you can see this because I forgot to make an important remark. It's obvious from the definition of F, right? Where did I put it? It's gone. Oh, here. It's clearly anti-symmetric in A and B, right? So that's clear when you interchange A and B. So I've used this property here because otherwise I wouldn't be able to write FDC as TCDG. So that property was crucial to be able to write this as TABD But you see that this is just the product of the matrix TA with TC, the BG elements, okay? So after some massaging, you discover that each term can be written in this nice way. And in fact, this is telling us that TA commuted with TC is IFACD Okay. So this is a remarkable fact that I already alluded to. I don't know who discovered this first. Again, I'm interested in history, so it's but I know very little about the history of mathematics. So TA, these matrices, so I said they're n by n matrices. Does TA form a representation? And in fact, it's n-dimensional representation, right? The n generators, and each one of them represented by a n by n matrix of the algebra. Because this is exactly the same as the equation up there, right? So the t's represent the x. So the x are, if you like, abstract generators, and the t's are concrete realization. And as you might have guessed, this is a famous representation. This is called the adjoint representation. So it's a little bit like in Moliere's comedy, in which the bourgeois gentilhomme realized that he's been writing prose all his life, or speaking prose. So many students suddenly realize they know the adjoint representation from the rotation group all their lives already. So the adjoint representation, as I said, are just these three antisymmetric matrices. But in general, this is you find that structure constants give a representation. And as another example is SU3. So SU3, the number of generators is 8. So this gives an 8-dimensional representation. So I hope this answers the student's question that why there was an 8-dimensional representation. Okay? So at this point, I would like to say a word about the adjoint representation in mathematicians' language. So I would just give a very little bit of space here. So the adjoint representation, one way the mathematicians think of the Lie algebra is that you can see XA commuted with XB gives you some XC. They say that XA is a map of XB to SC, XC, something like this. And the adjoint representation is one of the specific maps. Okay. Just to mention this, but I don't know enough about this. So Catán killing metric. Okay. So since we have a linear vector space, we can define a metric. And now the upper and lower indices do matter. And the Cartan killing metric is defined as trace of TATB. This is hardly surprising because physicists, we have all along been normalizing the Gell-Mann matrices, SU3 matrices. Yeah.
We draft, but the room is reserved for a spec seminar.
Oh, okay. At 1.
Now,
Oh, okay. So we'll stop here.
I'm sorry.
Yeah. So this is the Cartan killing metric. Okay.